Welcome to this deep dive on LLM Mesh, one of the most important architectural patterns emerging in production AI systems today. If you're building AI at scale, you've likely hit the ceiling of what a single large language model can do efficiently. LLM Mesh is the answer to that ceiling. Over the next 20 slides, we're going to cover everything from core architecture, intelligent routing, context propagation, federated deployments, security, cost optimization, and a full implementation roadmap. Let's get into it. What is LLM Mesh? At its core, an LLM Mesh is a decentralized, interconnected network of large language models, some specialized, some general purpose, that collaborate via standardized protocols to fulfill complex AI tasks that are simply beyond the capability of any single model. Think of it like a microservices architecture. But instead of services, your nodes are intelligent models. The three foundational properties are distributed, meaning no single model is a bottleneck, and compute is spread across specialized nodes. Collaborative, models share context, delegate subtasks, and aggregate outputs intelligently. And observable, you have full telemetry across every model call, every latency measurement, and every accuracy metric across the entire mesh. Why not a single LLM? This is the question every architect asks before adopting a mesh pattern. And there are 5 compelling reasons why a single LLM falls short in production. First, context window limits. Even the largest 200,000 token windows fail on enterprise workflows, requiring multi-step reasoning over massive corpora. Second, cost versus quality trade-off. Routing every single query to a frontier model like GPT-4 is prohibitively expensive, when smaller specialist models actually outperform on narrow tasks. Third, latency at scale. Synchronous single model calls create P99 bottlenecks that kill user experience. Fourth, domain specialization. A fine-tuned coding model, a legal reasoning model, and a summarizer will collectively outperform one general model on a mixed enterprise workflow. And fifth, vendor lock-in risk. Dependency on a single provider creates availability and pricing risk that a mesh abstracts away entirely. Core architecture overview. Let's walk through the full 3-tier architecture. At the top, you have your client or application layer. This could be a web app, an SDK, or an agent framework making API calls. Requests flow first to the mesh gateway, which handles authentication using JWT tokens, enforces rate limiting per user and tier, and performs initial routing classification. From the gateway, requests pass to the orchestrator, which is responsible for task decomposition and multi-step planning. It decides which models to involve and in what sequence. Below the orchestrator sit your 4 specialist model nodes: the code LLM for programming tasks, the reasoning LLM for complex logic, the domain LLM for fine-tuned vertical knowledge, and the embedding model for vector representations. All 4 nodes are backed by a shared infrastructure layer, comprising a vector database, a cache layer, an observability stack, and a policy engine that enforces compliance and routing rules. Every tier communicates over the same standardized API surface, making the whole system composable and replaceable at any node. The 4 layers of an LLM mesh. A well-designed LLM mesh is organized into 4 distinct layers, each with clear responsibilities. Layer 1, the infrastructure layer, is your compute foundation: GPU clusters, serverless inference endpoints, vector stores, KV caches, and the service mesh itself, running on something like Istio or Envoy, along with your observability stack. Layer 2, the model layer, is where your heterogeneous LLMs live. Open source models like Llama and Mistral, proprietary models like GPT-4 and Claude, and your own fine-tuned domain-specific models. Layer 3, the orchestration layer, is the intelligence layer. It handles task planning, multi-step reasoning chains, model selection logic, and the context handoff protocols between models. And Layer 4, the application layer, is what your consumers interact with. REST API is SDKs and agent frameworks like LangChain or AutoGen that expose the entire mesh as a single, unified LLM endpoint. Designing all 4 layers intentionally from day one is what separates a production mesh from a prototype. Intelligent Routing Engine. The routing engine is arguably the highest leverage component in your entire mesh. Here's how it works. Every incoming request hits the router first. The router runs a semantic classifier, typically a lightweight embedding model, to determine the intent and complexity of the request. It simultaneously runs a cost model that estimates the token cost of fulfilling that request on each available model. Then, factoring in 5 routing signals: task semantic similarity, token cost estimate, latency, SLA for that user tier, model availability and health, and user priority level. It makes a dispatch decision in milliseconds. A coding task routes to the code LLM. A complex multi-hop reasoning task routes to a frontier model. A domain-specific FAQ routes to your fine-tuned model. An embedding request routes to ADA or BGE. The router continuously learns from outcomes, improving its accuracy over time. Getting this routing logic right can reduce your cost by 60 to 75% while simultaneously improving response quality. Context propagation patterns. One of the hardest problems in a multi-model mesh is managing context across model hops. There are 4 established patterns, each with distinct trade-offs. Token passing is the simplest. You serialize the full conversation history and pass it to every downstream model. You get maximum fidelity, but the token cost grows linearly with every hop. Summarization. Compression uses a lightweight summarizer, LLM, to compress prior context before handoff. It's cost-efficient but inherently lossy and may drop critical nuance. Semantic memory, also known as RAG, retrieves only the relevant context from a vector store per query. This scales to unlimited history with no token budget waste, but retrieval quality becomes your critical dependency. Finally, structured state objects use a strongly typed JSON or protobuf state object that gets updated and passed through the pipeline. This gives you full auditability and type safety, but requires careful schema design up front. Most production meshes combine all 4 patterns, choosing the right one based on the task type and latency requirements. Orchestration patterns. How you orchestrate the flow of tasks through your mesh is as important as the models themselves. There are 4 core orchestration patterns you need to know. The sequential chain is your classic pipeline. Model A feeds. Model B feeds Model C. This is the pattern behind most RAG plus generation workflows and is the simplest to reason about. The parallel fan-out pattern decomposes a single task into n independent subtasks, executes them concurrently across multiple models, then merges results through an aggregator. This dramatically reduces wall clock latency for parallelizable workloads. Hierarchical delegation uses a planner, LLM, at the top that breaks down a complex problem, assigns each subtask to the most appropriate specialist model, monitors execution, and replans when a subtask fails. This is the foundation of production agentic systems. And the debate or critique loop pattern pits 2 models against each other on a problem. One proposes, one critiques, and a judge model selects the best answer. This is proven to significantly improve reasoning accuracy on complex analytical tasks. In practice, sophisticated workflows combine multiple patterns within a single request. Model selection strategy. Not all models are created equal for all tasks, and this matrix is something every architect should have internalized. Nanomodels, those under 7 billion parameters, are your best choice for intent classification and summarization. They're fast, cheap, and surprisingly accurate on narrow tasks. Small models in the 7 to 30 billion parameter range are good for summarization and excellent for tool and function calling. Large models between 30 and 70 billion parameters are your sweet spot for code generation and tool calling. They outperform frontier models on these tasks at a fraction of the cost. Frontier models above 70 billion parameters only earn their price tag on genuine multi-step reasoning and creative synthesis tasks. The key insight here is that most enterprise query traffic, typically 60 to 70%, consists of classification, summarization, and simple retrieval tasks that nano and small models handle perfectly. Sending those to a frontier model is simply burning money. Build your routing logic around this matrix and watch your cost per request drop dramatically. Observability and telemetry. You cannot run a production LLM mesh without deep observability. The three pillars are traces, metrics, and logs. And in a mesh, each one is more complex than in a traditional microservices system because you have non-deterministic, latency variable model calls at every hop. For traces, you instrument every model invocation with open telemetry spans, propagating a trace ID across all synchronous and asynchronous hops. This gives you full request lineage. You can see exactly which models were involved, in what order, and where latency was introduced. For metrics, your critical KPIs are latency histograms at P50, P95, and P99 per model node, token throughput, and cost per request, model hit rate, and routing accuracy, and error rates, and retry budgets. For logs, every inference call should emit a structured JSON log with fields including model ID, input token count, output token count, latency in milliseconds, routing reason, and cache hit status. Your target benchmarks for a well-tuned mesh are 94% routing accuracy, 67% latency reduction versus a single model architecture, and 60 to 75% cost reduction. You can only hit those numbers if you're measuring them. Security and access control. Security in an LLM mesh is multi-layered and cannot be an afterthought. Let's walk through each layer. Authentication and authorization uses mutual TLS between all mesh nodes, JWT tokens, validated at the gateway, and role-based access control per model, meaning lower-tier users simply cannot access frontier models. The prompt injection guard is a dedicated input scanner, itself a lightweight LLM, that validates every incoming request for injection attempts before routing it downstream. This is a critical defense layer that most organizations skip and later regret. Data residency is enforced by a policy engine that geo-routes requests based on data classification. Personally identifiable information stays on premises. Non-sensitive data can go to cloud models. This is your GDPR and HIPAA compliance mechanism. Model watermarking applies cryptographic signatures to outputs for full audit trails and detects model impersonation attacks in federated deployments. And rate limiting uses per user, per model, per tier token bucket algorithms at the gateway to prevent both accidental and malicious cost explosions. These controls must be designed in from day one. Retrofitting security onto a mesh in production is painful and expensive. Federated LLM Mesh. Federated LLM Mesh extends the architecture across organizational, cloud, and regulatory boundaries without centralizing raw data. And this is where the pattern becomes truly transformative for the enterprise. In a federated topology, Org A runs models on premises, Org B in a private cloud, and Org C in a public cloud. All three participate in the mesh through a federated coordination plane that enables privacy-preserving inference, differential privacy mechanisms, and secure aggregation protocols. The critical principle is that raw data never leaves an organizational boundary. What gets shared are model gradients, outputs, and aggregated signals, never training data. This makes the pattern compliant with GDPR, HIPAA, and SOC2 by design. The bidirectional dashed lines between organizations represent peer-to-peer mesh connectivity. Each org can consume capabilities from the others without exposing its underlying data. And crucially, this architecture enables cross-organizational LLM fine-tuning via federated learning. Multiple organizations can collaboratively improve shared models without any party exposing their proprietary data to the others. Caching strategies. Caching is one of the most underutilized cost optimization levers in LLM systems. In a mesh, you have 4 distinct caching tiers that work together. The exact match. Cache computes a SHA-256 hash of the normalized prompt and returns cached responses for identical inputs. For deterministic FAQ and support workloads, this can achieve over 90% hit rates with negligible infrastructure cost. The semantic cache embeds the query and retrieves cached responses for semantically similar prompts above a cosine similarity threshold, typically 0.97 or higher. This handles paraphrased versions of common queries and typically achieves 40 to 60% hit rates in production. The KV cache or prefix sharing tier shares attention key value caches across requests with common system prompts. This is native to inference frameworks like VLLM and TensorRT-LLM and delivers significant GPU compute savings without additional storage cost. Finally, response fragment caching caches subsegments of structured outputs, like boilerplate sections in generated reports, and stitches them together at response time. Combining all 4 tiers in a well-tuned mesh can reduce your inference compute costs by 40 to 60% for typical enterprise workloads. Failure modes and resilience. Every distributed system fails, and a mesh of LLMs is no exception. You need deterministic mitigations for each failure mode before you go to production. Model node down is handled by a circuit breaker pattern with automatic fallback to a backup model, combined with health checks every 10 seconds. Context. Window exceeded is handled by chunking middleware that automatically splits oversized inputs, with a summarizer model compressing overflow context before it hits the target model. Hallucination cascade, where one model's incorrect output poisons downstream models, is mitigated by a critic model that validates each hop's output against a confidence threshold, triggering a retry with a different model if the threshold isn't met. Routing loops are prevented by a hop counter, TTL, embedded in every task object. The default is 5 hops maximum, configurable per workflow. And cost explosion is controlled by hard token budgets per request, with an escalation alert at 80% of budget and an automatic kill switch at 100%. The key principle is that every failure mode must have a deterministic, automated response. Humans should only be involved for systematic failures, never individual request failures. API and integration design. How you expose your mesh to consumers is as important as the mesh itself. The single most important design decision is to implement an OpenAI-compatible API surface at your gateway. This means 0 SDK changes for any consumer already using the OpenAI Python SDK, TypeScript SDK, or any OpenAI-compatible library. Your core endpoints are the standard post/v1/chat/completions, post/v1/embeddings, post/v1/completions, and get/v1/models, plus one mesh native endpoint, post/v1/mesh/root, for consumers that want explicit control over routing behavior. On top of this synchronous surface, you layer async and streaming patterns. Server-sent events. Streaming is non-negotiable for any user-facing application. Token-by-token streaming dramatically reduces perceived latency. WebSocket bidirectional connections support agentic loops with real-time human-in-the-loop interrupts. Async job queues handle long-running batch inference workloads, with results delivered via polling or webhook callbacks. And GraphQL subscriptions serve event-driven frontends that need to react to mesh state changes in real time. The right integration pattern depends on your latency requirements, workload type, and consumer architecture. Cost optimization framework. Let's talk about the numbers that make CFOs pay attention. Looking at cost per million requests across 4 common task categories. The difference between a single LLM architecture and a properly routed mesh is stark. For simple queries, a single frontier LLM costs $8.50 per million requests. A mesh routes those to nanomodels and brings that cost down to $1.20, a 86% reduction. For code generation, you go from $7.20 to $3.10 by routing to mid-tier coding specialist models. For multi-step reasoning, the one-place frontier models genuinely earn their cost. The reduction is more modest, from $9.80 to $6.40, because frontier models are still the right choice here. And for summarization, the savings are dramatic again. $6 down to 90 cents by routing to small, fast summarizer models. The overall average across a typical enterprise workload mix is 60 to 75% cost reduction. That's not a marginal improvement. For organizations running millions of LLM calls per day, that's millions of dollars in annual savings. The mesh pays for itself very quickly. Reference architecture. Enterprise. Let's map this to a concrete technology stack you can actually deploy. On the left, your application stack runs top to bottom. Client SDKs and UI at the top. Your API gateway runs on Kong or API SIX, handling authentication, rate limiting, and the OpenAI-compatible API surface. The mesh orchestrator is built on LangGraph or a custom orchestration layer, handling task decomposition and model selection. Below that, your model registry and router maintains the inventory of available models and executes routing decisions. The inference cluster runs on VLLM or TGI, text generation inference, for high throughput, batched model serving. And at the base, your data plane combines a vector database, caching layer, and object storage. On the right, your ecosystem tooling breaks down by function. For orchestration, LangGraph, AutoGen, and Crew AI. For inference, VLLM, TGI, Triton, and Allama for local development. For observability, Langfuse and Phoenix for LLM-specific tracing, backed by Grafana and OpenTelemetry. For vector storage, Qdrant, Weaviate, Pinecone, or PG Vector, depending on your scale and infrastructure. And for the service mesh layer, Istio, Envoy, or Linkerd. Every component in this stack has been battle-tested in production at scale. Implementation roadmap. Here's how you actually build this in a real organization over 13+ weeks. Phase 1. Foundations. Runs weeks 1 through 4. You audit your existing LLM usage and costs to understand your baseline, define your mesh topology and node types based on your actual workload mix. Deploy your API gateway with basic routing and instrument baseline observability so you have something to measure against. Phase 2. Core Mesh. Runs weeks 5 through 8. You build the orchestration layer, integrate your first 3 to 5 specialist models, implement semantic caching, and add circuit breakers and fallback logic for resilience. Phase 3. Optimization. Runs weeks 9 through 12. You fine-tune your routing model on real production traffic. This is where routing accuracy jumps from 70% to 90+%. You add federated deployment for data residency requirements, implement the full cost optimizer with smart tier routing, and complete your OpenTelemetry tracing and alerting setup. Phase 4. Scale and govern. Starts at week 13 and is ongoing. Multi-region mesh federation, self-healing orchestration loops, model performance, A/B testing framework, and executive cost and quality dashboards. The key principle throughout is to deliver value at each phase. You should be saving money and improving quality from week 5 onwards, not waiting until the full system is built. Emerging trends in LLM Mesh. The LLM Mesh landscape is evolving rapidly. Let's look at where things are headed. Model as a service mesh is happening right now. LLMs being exposed as versioned microservices with explicit SLAs, blue-green deployment, and canary releases. This is the natural convergence of ML ops and cloud-native engineering practices. Agentic mesh topologies are emerging. Architectures where autonomous agents route their own subtasks to other agents, creating self-organizing meshes with no static orchestrator. This is where LangGraph and AutoGen are heading. Neuromorphic routing is experimental, using a meta LLM trained on mesh telemetry to make routing decisions, continuously self-optimizing based on real performance data. Early results are promising. Quantum-assisted inference is in active research. Quantum annealers optimizing token batch scheduling and routing decisions at nanosecond latency windows. Still years from production, but worth watching. Embodied LLM Mesh extends the pattern to physical systems, robots and IoT sensors as mesh nodes, with LLMs receiving real-world sensor inputs and coordinating actuation. And regulatory mesh compliance is imminent. EU AI Act and NIST AI RMF enforcement layers, built directly into the mesh policy engine, with automated compliance reporting. The organizations building mesh infrastructure today will be well-positioned as these trends mature. Key takeaways. Let's close with the 5 things you must take away from this video. 1. Mesh beats monolith. No single LLM is optimal for all tasks. A well-designed mesh of specialists will outperform a single frontier model on quality, cost, and latency simultaneously. 2. Routing is everything. Your routing engine is the highest leverage component in the entire architecture. Invest in making it accurate, observable, and continuously learning. 3. Observability first. Design your telemetry stack before you write a single line of orchestration code. You cannot optimize a distributed AI system you cannot measure at every hop. 4. Start narrow, scale wide. Begin with 2 or 3 models solving one specific workflow. Prove the economics. Then expand based on real cost and quality data, not theoretical projections. And 5. Security is non-negotiable. MTLS, RBAC, prompt injection guards, and data residency enforcement must be designed in from day one. Retrofitting security onto a production mesh is painful, expensive, and leaves you exposed in the meantime. If this video was valuable, please like, share, and subscribe Quantum Tech Sage. There's much more AI architecture content coming. Thanks for watching.